Welcome to 7.9 Slant Asymptotes. So again, before we get started, I'm going to do a brief overview of Frady. Remember, F is standing for factor. We're going to factor the numerator and the denominator. R is for roots. We're going to set our numerator equal to 0 to get our x-intercepts. A is for asymptotes. We're going to set our denominator equal to 0 to get our vertical asymptotes. Remember, these are lines that we cannot cross. T is for twins. We are looking for identical factors in the numerator or the denominator. If they happen to be in the numerator, we're going to have tangency. If they happen to be in the denominator, we are going to have togetherness. E is where we're going to focus on today. So far we've only dealt with the BOBO, the bigger on bottom, where we got a horizontal asymptote of y equals 0, and the eats DC, where it was exponents are the same, therefore we divided the coefficients, and that gave us our horizontal asymptote. Now the third case, which is what we're going to be doing today, is BOTSA. Bigger on top, our horizontal asymptote is actually going to be a slant asymptote, meaning that it's going to have a slope to it. So in order to get this horizontal asymptote, we're going to have to divide to get the slant asymptote, and we are going to ignore the remainder. So I'm going to talk about this a little bit in the lesson, but basically the reason why we ignore the remainder is E is going to stand for end behavior. So we're interested in what's happening as we get out to negative infinity and positive infinity. So when those numbers get really big and really small. When we get to this remainder part, it really does not make a difference, which is why we ignore it. Y is our y-intercept. We're going to plug in x equals 0 and solve, giving us our coordinate point for that y-intercept. So let's go ahead and get into the notes. The first thing we're going to do is a quick recall on how to divide a polynomial, because we'll need that in order to find our slant asymptotes. You have two methods you can do. The first one is long division, and long division is going to always work. You never have to look for certain features. If you put it into long division correctly, it is going to work. So I'm going to set up my long division. So I have x squared, and I'm going to fill in 0x because I am missing a term, minus 4 divided by x. So the first thing you want to see is, what do I have to multiply the divisor by to get the first term of the dividend? So I have to multiply x by x to give me x squared. So I get x squared down here, and I'm going to subtract x squared minus x squared is 0. Going to bring down my first term, 0x. Can't do anything with that yet, so I'm going to go ahead and bring down my second term, minus 4. X can never be multiplied by anything and get negative 4, so this is going to end up being my remainder. So my final answer for this problem would be x plus negative 4 over x. Now here was one option for how you could do it. Another option is you could use synthetic division. Now something you have to be careful of with synthetic division is it only works when your divisors are x plus k or x minus k, where k can be any number. It can't be anything else. It can't be 2x plus 1. It can't be x squared plus 1. It has to be x plus a number or x minus a number. What's nice about this problem is we can think of this as x squared minus 4 over x plus 0, which is what I do for this synthetic division. Now, first thing you want to do is set up your box method. Remember, you're going to set your divisor equal to 0 in order to get your number in the box, so it ends up being 0. And then you write out the coefficients of your dividend. So I have 1, and then I would have a 0, and then I have a negative 4. So I have 1, 0, negative 4. First thing you do is bring down your first number. So I bring down my 1, multiply it by the box. So 0 times 1 is 0. Add these two things together, which gives me 0. 0 times 0 gives me another 0. Add these two things together, I get negative 4. The last number in your synthetic division is always going to be your remainder. So because I'm doing the same problem, I do end up with the same answer. So, just to reiterate why we ignore the remainder for slant asymptotes, with the remainders of division, we are always dividing it by the divisor. So, in this case, it's x. If I were to look at x as it approaches positive infinity, I'm going to get -4 over a million. That's a really, really, really tiny and insignificant number. It's not going to change the overall behavior of this line. So that is why we ignore it. And we're going to get into this more in 7.10 when we start to talk about limits. So let's go ahead and look at the features for example 1. So remember, F stands for factor. So I'm going to factor the numerator and the denominator. So I have x plus 2, x minus 2 over x. R stands for roots. I'm going to set my numerator equal to 0. That's going to give me two roots, one at -2, 0, one at +2, 0. A stands for asymptotes. Going to set my denominator equal to 0. Gives me one vertical asymptote at x equals 0. T stands for tangency and togetherness. So I'm looking for twins either in the numerator or the denominator. And I don't have either of those for this problem, so I have no tangency and no togetherness. Now, E is going to be my end behavior. So I'm going to be looking at my highest exponent in the numerator and the denominator. So first thing I want to do is look at the highest exponent in my numerator, which in this case is 2. And then I look at the highest exponent in my denominator, which in this case is 1. So it's bigger on top. I'm going to have a slant asymptote. Now, remember, when I have a slant asymptote, I must divide and I must ignore the remainder. Now, we have already divided for this problem. This is the problem we did in our recall. Now, we got x plus -4 over x. Remember, we're ignoring the remainder, so because of that, my horizontal asymptote is y equals x. Now, I will graph this as a line with a slope. Sometimes we'll have plus or minus. That's just going to mean a shift up or down. So because of this, my y equals x is graphed with a dotted line. Now, for my y-intercept, based on the fact that I have a vertical asymptote at x equals 0, I can kind of determine that I'm not going to have a y-intercept, but I went ahead and verified anyway. I ended up with -4 over 0, which is undefined. Therefore, there is no y-intercept. Now we have to graph our curves. This is typically the hardest part. It does not have to be that difficult. Remember, you want to look at how many vertical sections do I have? Well, I have one vertical section here and another vertical section here. So I should have two curves on my graph. The only difference between having a horizontal asymptote and a slant asymptote is you're going to have to look at your top and bottom sections a little differently. I have one top section here, one bottom section here. And then on my right-hand side, I have one top section here, one bottom section here. All of the same rules apply. If I have an intercept, I have to go through it. I cannot cross any axes without an intercept there, and I cannot cross any vertical asymptotes. So let's go ahead and focus on my first vertical section. So I can either place my curve in the top or in the bottom. Now, if I place my curve in the bottom, it fits, but I run into the issue of this x-intercept being ignored. I don't want that to happen. So it's not going to work in the bottom. Instead, it has to run along my slant asymptote, go through my x-intercept, and come up my vertical asymptote. Now, remember, this graph does not have any togetherness, so I know that my second piece needs to start at the bottom, needs to come up through my x-intercept and come out along my slant asymptote. So there I go. I have two vertical pieces and two curves on my graph. So let's start with the easier one. Vertical asymptotes come from setting our denominator equal to 0. So I take 2x minus 3, set it equal to 0. I get a vertical asymptote at x equals 3 over 2. Now, our horizontal asymptote comes from end behavior. End behavior focuses in on the highest term in the numerator and the denominator. So I have 4x squared over 2x to the power of 1. Remember, we're looking at how do the highest exponents compare. I have a bigger on top, which is telling me that I'm going to have a slant asymptote. So bigger on top, slant asymptote, meaning we have to divide and we're going to ignore any remainder that we may get. So the first thing I notice is my divisor is of the form 2x minus 3. Because it's in this form, I cannot use synthetic division. I have to do long division. So I'm going to go ahead and set that up. I have 2x minus 3 dividing 4x squared plus 10x minus 23. First thing I have to ask myself is, what do I multiply 2x by to make 4x squared? And the answer is 2x. So I'm going to take 2x and I'm going to distribute it to both terms. And I'm going to get 4x squared minus 6x. I do some subtraction. This is going to go away. 10x minus negative 6x is going to give me 16x. I bring down my negative 23, and then I ask myself, what do I have to multiply 2x by to make 16x? That's going to be plus 8. Going to go through the same process, multiply 8 times both terms. That's going to give me 16x minus 24. I subtract. I get a 1 left over. What can I multiply 2x by to make 1? Well, nothing. And because of that, this would normally, in regular division, be considered my remainder. It is my remainder. But for the sake of finding slant asymptotes, we are going to ignore this. Focus in on what we have wholly. And that means our slant asymptote is going to be y equals 2x plus 8. So it's going to have a slope of 2, and it's going to be shifted up 8 when I were to graph it. Okay, example 3. So I first notice my numerator has a GCF. So I'm going to pull that out first before I get into my factoring step. My numerator factors to be x plus 2, x plus 2. My denominator factors to be x plus 4, x minus 2. So my roots come from my numerator. I have 2. I have 1 at 0, 0, and 1 at negative 2, 0. My asymptotes come from my denominator. I have 2, 1 at x equals negative 4, and 1 at x equals positive 2. My tangency and togetherness, I notice that I have a set of twins. X plus 2 and x plus 2 are identical. So that means because it's in the numerator, I'm going to have tangency at that x-intercept. And I always like to make a note on my graph so that I don't forget tangency is going to happen there. A bounce at this point is going to occur. And I don't have any togetherness because there's no twins in the denominator. Now I'm going to kind of do my end behavior over here because I'm noticing that I have x cubed over x squared. It's bigger on top, so I'm going to have a slant asymptote, meaning I'm going to have to divide. So I went ahead and kind of showed you everything first, and I'm going to kind of walk you through what I did. So first thing I did was I set up for long division because my divisor is not of the form x plus k or x minus k. So then I ask myself, okay, what do I have to multiply x squared by to make x cubed? That answer is x. So I take this x and I distribute it to every term, and that's going to give me x cubed plus 2x squared minus 8x. So I subtract that, and I end up with 2x squared plus 12x and plus 0. So then I ask myself, what do I multiply x squared by to make 2x squared? Well, I multiply it by plus 2. So I take my plus 2, I distribute it to every single term, and I get 2x squared plus 4x minus 16. Then I do my subtraction, and I'm left with 8x plus 16. Well, there's nothing I can multiply x squared by to get 8x, so this ends up being my remainder. But again, we ignore the remainders for slant asymptotes, so my slant asymptote ends up being y equals x plus 2. It's going to have a slope of 1, and it's going to move up 2. Now, in my graph, I don't typically connect my end behavior in my middle sections. If you were to do that, it would be perfectly fine, especially when you are getting the hang of graphing these types of problems. I'm moving up from the origin 0, 0. Because of this plus 2, everything shifts up 2, and I end up with just a slope of 1 in either direction. So you can have your dotted lines kind of continue in here if you like. Just remember, they don't have the same rules as vertical asymptotes. We can cross them, and most likely in the middle section, you will end up crossing them. But I'm going to take them off my graph for now. And my y-intercept, even though I know kind of what it is already, I'm going to verify that. When I plug in 0 everywhere I see x, I end up with 0 over -8, meaning my y-intercept is at 0, 0. So let's go ahead and work on placing our curves on our graph. So again, I always like to see how many curves should I have overall. I have one vertical section here, another here, and another here. So I should have 3 pieces. One piece in this section, one piece in this section, and one piece in this section. Now, again, we have to follow the rules of if there are intercepts, we have to go through them. If there are no intercepts, we cannot cross an axis, and we cannot cross any vertical asymptotes. So my first decision comes, should I place my curve in the top, or should I place my curve in the bottom? Well, one thing I notice, if I place it in the top, I would be crossing the x-axis where there is not an intercept. Cannot have that happen. So because of that, this curve has to go down below. And I know that I don't have any togetherness for this graph, so I know my next piece has to start up top. It's going to come down, touch my x-intercept. Now remember, when we have tangency, we're not just going to go through the point. We're going to touch the point, bounce off of it, and again, I notice I still have to go through this point. So I kind of bounce off of this, and then I come back down, and then I'm going to go through because that point does not have tangency, and I get kind of a nice curved, almost S-shaped looking piece, but not quite. Now for my third piece, again, I'm running into that same issue of if I were to place it here, I would not have a x-intercept cross through, so the only option I have is up here in this top section. And now I have 1, 2, 3 curves for my graph. Example 4, we are creating a rational function that has the following characteristics. And we already have one note made, but I do have a couple more. I'm not even going to focus on the graph right now. We're just going to focus on what we've been told. Roots at -2, 0, 3, 0. Roots are always going to be in the numerator. Vertical asymptotes come from the denominator. Slant asymptotes depend on the highest exponents, and y-intercepts are typically our last check. So what I always like to do is I like to start with my roots and my vertical asymptotes. I set out a y equals, I give myself a big fraction bar, and I start to work in reverse. If I had a root at -2, I know that's coming from the factor x plus 2. And if I had a root at 3, I know that's coming from the factor x minus 3. Both of these have to be in the numerator. Vertical asymptotes at x equals 1. That means I had a factor in my denominator of x minus 1. And to verify my slant asymptote, I do have to deal with this in standard form. Typically, for problems like these, we usually tell you to leave it in factored form, but if you are given a slant one, you do want to verify that it works out. So I went ahead and multiplied my numerator to give me x squared minus x minus 6 over x minus 1. Did some synthetic division. X minus 1 gives me a positive 1 in the box. My coefficients are 1, -1, -6. Bring down my first number, which is 1. 1 times 1 is 1. 1 plus -1 is 0. 1 times 0 is 0. -6 plus 0 is -6. Remember, this last number is our remainder. So it does work out that I end up with the slant asymptote of y equals x. And my last check is to verify the y-intercept. So I plug in 0 everywhere I see an x. I get -6 over -1, which gives me a y-intercept of 0, 6. So my final answer could either be accepted as y equals x plus 2 times x minus 3 over x minus 1, or you could do the multiplied version, y equals x squared minus x minus 6 over x minus 1. Now, just to do a quick review on curves, since I know that tends to be the issue we have with graphing these, I went ahead and placed all of these features on a graph, and I'm going to work through where to place the curves for this problem. So I have one vertical section, I have two vertical sections, meaning I should have two curves. And I noticed that I don't have a y-intercept in my bottom section. So it has to start in the top, go through, because I don't have any tangency, go through my y-intercept, come up to my vertical asymptote, but do not cross it. And then there's no togetherness, so I know this piece starts down here, goes through my x-intercept, up along my slant asymptote, two vertical sections, two curves. That is my graph for my created problem.